So let's see if we can play with this factoring idea a little bit here. So just to kind of give us an example to work through, let's take a look at this number 56. Now there's a number of different ways I could factor 56, right? That I could write 56 as the product of two smaller natural numbers. And for what we're going to be doing, it doesn't matter where you start, right? So I'm going to say, like, 56 is 7 times 8. Now, 7 is prime. Okay, there's really nothing I can do with 7. 8, on the other hand, 8 is a composite number. So I could factor 8, break 8 down, if you will, to 4 times 2. Right? So 56 is 7 times 4 times 2. And, okay, I'm done with the 2, right? 2 is prime, so there's nothing more I can do with that. But that 4 is also composite. All right, so I can rewrite the 4 as 2 times 2, and I end up with this. And now at this point, I can't go any further. Right? 7 and the 2's, those are all prime numbers. So there's no more factors I could split out, if you will, here. Okay, once you've done this, once you've rewritten a number as just a bunch of prime numbers, you have what's called the prime factorization of the number. So I've got a little information about those prime factorizations here. It's something called the fundamental theorem of arithmetic, and it answers two big questions that mathematicians love to obsess about, right? First one is existence, and the second one is uniqueness. So what this theorem says is, first, every composite number has a prime factorization. That's the existence part. And the second thing it says is that prime factorization is unique. There is only one way to do it. Now, I say that, and I can see some people out there, you're thinking this through, and you're saying, okay, wait a minute, professor. The order of the factors doesn't matter. Right? So the prime factorization of 6, for example, is 2 times 3. Some of you may be thinking, oh, yeah, well, wait a minute, what about 3 times 2? We're going to call those the same thing. Right? So it's unique up to the order of the numbers. So suppose I give you a number, like 420, and I ask you to find its prime factorization. Okay, there's two methods we can use to do this. One is called the tree method. The other one is called the division method. Doesn't matter which one you use. And I really encourage you to take that attitude with your students if you're teaching this to people. Show them both methods. Let them pick the one that works for them. You don't really get anything from knowing how to do both of these methods. You might as well just pick your favorite and run with it. Okay, so here's how this works. I'm going to look at 420, and I'm going to find two factors of it. Which two factors you pick doesn't matter. You're going to end up at the same place regardless. Now, when I look at a number like 420, the first thing that jumps out to me is that 0 on the end. All right, that tells me that I can take a 10 out of this really easily. 420 is just 10 times 42. Okay, both of those numbers are composite. Right, we haven't hit primed yet. So I'm going to keep building my tree further and further down. If you look at that 10, for example, 10 is 5 times 2. Those are both prime numbers. Right? So I can't go any further. Those branches are done. Right? Jump back over to the 42 side. 42 it ends in a 2, so it's even. At the very least, I can take a 2 out of it. When I looked at this the first time I was putting these slides together, that's not what came to my head first. What came to my head first was 6 times 7. If you want to do 2 times 21, awesome. You're going to end up in the same place. And now we're almost done. 7 is prime. 6 is not. I can rewrite 6 as 2 times 3. And now I can't go any further. Now all of my branches have kind of bottomed out in prime numbers. So now I'm ready to get my answer. If you look at those prime numbers in graph theory, we talk a lot about trees like this. We would call them leaves, right? And leaves are those very bottom elements. Those are the prime numbers that make up the prime factorization of 420. So what I'm going to do is I'm going to take all of them, and because I'm a math professor and we're a little uptight this way, I'm going to put them in order, right? I'm not going to do 5 times 2 times 2 times 3. I'm going to do 2 times 2 times 3 times 5 times 7. And yeah, okay, that's really close. But again, just as a math person, I wouldn't stop there. I can make this just a little simpler using some exponents. 2 times 2, that's 2 squared, right? So that will be my final representation for this. I would say the prime factorization of 420 is 2 squared times 3 times 5 times 7. So let's try another one here. Let's see if we can find the prime factorization of 180. This time, using the other method I mentioned, we'll see if we can do this using the division method. To use the division method, what you're going to do is you're going to repeatedly divide by prime numbers, right? And it's certainly easiest if you start at the beginning. Smallest prime number is 2. Does 2 go into 180? Yes. 180 divided by 2 is 90. Okay, now look at the 90. 2 also goes into 90. So 90 divided by 2, that's 45. Does 2 go into 45? No. So we've pulled all the 2's that we can out of this thing. So now you move on to the next prime number. Right, you're going to jump up to 3. Does 3 go into 45? Well, yes. 45 divided by 3 is 15. 3 also goes into 15, and when you do that, you end up with 5. This is how you know when to stop. Right, when you do this division and you get a prime number, you're finished. Right, can't go any further. So to get our final answer, to get the prime factorization, we're going to look at all of those prime numbers that we divided by plus the final one that we ended up here. Right, so if we multiply all of those together, the prime factorization of 180 is 2 times 2 times 3 times 3 times 5. But just like we saw in the previous example, I can shorten this up a little bit using some exponents. Right, so I'll make this 2 squared times 3 squared times 5. And that would be my final answer. So, like I said earlier, and I really want to kind of emphasize this, there is no advantage to using one method over the other. There is no advantage to knowing both of these methods. This is really a case where I would have no problem letting students figure out which one they're most comfortable with and stick with it to the exclusion of the other one. Okay. Personally, I have a bit of a preference for the tree method. The division method is a little more demanding in that you have to have this list of prime numbers in your head. You have to know you start with 2, then 3, not 4 because 4 isn't prime, so you got to jump to 5, not 6 because 6 isn't prime and you already did 2 and 3, so jump to 7, skip 8 and 9 and 10 and 11. You have to have this list of prime numbers to work with. Once you've been doing this for a while, you can, in your head, make a list of the smaller prime numbers, not too difficult. But with the tree method, do whatever you see first, right? I started with, 42 times 10? Neither of those are prime. Those are both composite numbers, and it worked out just fine. Okay, so I'm looking ahead. In the next lecture, we're going to look at some things we can do with these prime factorizations.